Okay, let's get into Unit 4, which talks about parallel and perpendicular lines. We'll apply what we've learned about lines and angles, and we'll get more into proof, especially in this lesson. We briefly touched on proof in Unit 2, so we'll get into that a lot more because that's an important topic as we use logic to explain different theorems and postulates. So let's get started. Proof. Proof is a logical argument that shows that a statement's true. Several different formats. First one we'll take a look at is the two-column proof, which has numbered statements and corresponding reasons to present an argument in a logical order. We have that example down here that we'll go through. The two-column proof, the left-hand column, is either given information or the result of applying a known property or fact to statements that have already been made. So they flow in order logically, and they're just numbered in the way that whoever's designing the proof writes them down. They can be written in different orders as long as it flows logically. And then on the right-hand column, we have reasons that correspond to each statement. So how do I know I can state that? Here's the reason to back it up. So another type of proof that we'll take a look at is a paragraph proof. We'll talk about that later on in the lesson. Then we'll also get into flow proofs in later units as we learn more about proof. So the big thing about proof is that just pick a way that you can present a logical argument to prove a statement true. So in this first case, we want to prove that AB is congruent to BC. So we want to show that these two are congruent. We can't say they are because they don't have markings to prove it. All we know is our given information, that AC equals AB plus AB. So I know this full segment equals AB plus AB again. So how do we show that these two are the same? Well, let's start off with what we know. Typically, that's how proofs start off. Let's write down the given information. Okay, now from that, what can I conclude? There's not much I can conclude from the first statement, but looking at the diagram, I know that AB plus BC equals AC because that's the segment addition postulate. And we've learned that before. Next, after I take a look at those two statements, I can logically conclude that, well, AB plus AB equals AC, and AB plus BC equals AC. Since they both equal AC, by way of the transitive property, I can say that these two segments, or these two statements, are equal. So I go ahead and write down that this is the transitive property as my reason. The transitive property. Oops, the pen's getting crazy here. Transitive property of equality. Okay, and then from there, I see that I have AB on both sides of the equation. So if I just subtract AB, just like we do in algebra, subtract the AB over here, and I can subtract the AB on the left side of the equation also. And what am I left with? AB equal to BC. And so that's just that subtraction property of equality that we use in algebra. And we can apply that in geometry too, anytime we're dealing with an equation. So I'll just abbreviate here. That's the subtraction property of equality, would be the corresponding reason to go with that last statement. That's a two-column proof, just a listing of logical statements in order and their corresponding reasons that go with them. Okay, so as we talk about segment congruence, we can use the reflexive, symmetric, and transitive properties. And for any segment AB, well, the reflexive property says that AB is congruent to segment AB. We can state that a segment's congruent to itself. A symmetric property, if AB is congruent to CD, well, I can flip the order if I like and say segment CD is congruent to segment AB. And by way of the transitive property, if AB equals CD and CD is congruent to EF, then, well, I know AB is also congruent to EF. And the same thing will apply with angles. So if I have an angle A, I can say, well, angle A is congruent to itself. It's a step that I can write down in a proof to prove if it's part of two different angles. I can also say that, well, if angle A is congruent to angle B, I could say it the other way and say angle B is congruent to angle A. And transitive property if angle A is congruent to angle B and angle B is congruent to angle C, well, then angle A has to be congruent to angle C because they're all congruent to each other. So those are different properties that we'll use, so it'll be good for us to recognize how to write those and when to use them. So the first example, angle R is congruent to angle T is congruent to angle P, angle R is congruent to angle P. That would be the transitive property because they're all equal to each other. If segment NK is congruent to segment BD, and if segment BD is congruent to NK, so we're just flipping those around, that would be the symmetric property of equality. Think of symmetry. It's the same on both sides, so you just flip it over. All right, so let's apply some of these properties of equality. Okay, so first of all, look at our diagram. We know that BD bisects angle ABC. We want to prove that measure of ABC is 2 times measure of angle 1. So what do we know? Well, BD bisects ABC. Okay, so we'll write that down. That's the information we know right off the bat. And why do we know it? Well, it's our given information. We're told that that's true. Next, well, what do we know about angle bisectors? Well, if it's an angle bisector, well, we know that these two angles have to be congruent. So angle 1 is congruent to angle 2. And why do I know that? Well, that's just what an angle bisector does. So if you know by definition what something is, you can just write down what is true and then just state that that's the definition of an angle bisector. That's what it does. So now, since we want to talk about finally and prove that angle ABC is equal to 2 times measure of angle 1, we need an equation. So we need to convert this to an equation. So we can just say the measure of angle 1 is equal to measure of angle 2. Because we know congruent angles are equal to the measures of the angles. So definition of congruent angles when we want to use the equations. Now, measure of angle 1 plus measure of angle 2 equals measure of angle ABC. How do I know that's true? Well, can't you see that the two smaller angles equal the bigger angle? So that would be the angle addition postulate that we talked about back in Unit 1. Okay, so now we still need to prove that that big angle is double this angle 1. So how are we going to do that? Well, remember that we've proven that 1 and 2 are the same. So if we want to prove that we have double angle 1, let's substitute angle 1 in for angle 2 here. So let's put angle 1 in its place. So measure of angle 1 plus measure of angle 1 equals measure of angle ABC. So we're just substituting. And then finally, if I know measure of angle 1 plus measure of angle 1, that's the same as 2 times the measure of angle 1. And so we're just simplifying that part of the equation, and we're flipping the equation around to make it match how it looks in the final proof. And say measure of angle ABC is equal to 2 times the measure of angle 1. And there we're just using the distributive property to simplify that down. Okay, so just another summary of how a two-column proof works. So proving the symmetric property of the segment congruence. If I know AB is congruent to CD, I want to prove CD is congruent to AB. So we're just proving that symmetric property. Seems kind of a odd thing to prove, but if we can list the proof for it, we know it's true all the time. So first thing you want to do is copy or draw diagrams, label information. That's going to help you develop proof, because if you can see what's going on, that helps you use your logical reasoning and figure out how to get to the proof statement. So typically we want to put down our given information first. Just put it all in writing first so that we can move from there. So that's given. And keep in mind that the number of statements varies. If you can prove it in less statements, that's fine. But if you use more, there's more than one way to prove it. So after we know AB is congruent to CD, well, congruent segments, we know AB equals CD, and that's just definition of congruent segments. I know they're congruent, so they have to be equal. Their measures are equal. And if I don't like the way it's written, AB equals CD, remember I can switch it around. CD equals AB. That's the symmetric property of equality. We know we can flip things around. The equal sign just means the same as. So we can put things on different sides if we'd like. And then from equal, we can say, well, the segments have to be congruent, because that's the definition of congruent segments. So always give a reason for your last statement, and make sure that your last statement is what you're trying to prove. And you'll use different definitions, postulates, or theorems to help you along the way. Okay, so let's do some practice with this one. Go ahead and try this one on your own. Pause the video and start it again when you're ready. Okay, so the first thing I did after reading the problem was I drew a diagram to represent rest area A, the Rice exit, the Mason exit, and rest area B. And then I showed the relationships that I knew. Well, I knew that the rest area was halfway between the Rice exit was halfway between rest area A and the Mason exit. So I put a tick mark there to show that those segments were congruent. And then I also knew that the Mason exit, the same distance between A and the Rice exit. So between B and Mason was the same as these. Since these already had a tick mark, this had to have one. So I need to go down and write how I know that the Mason exit's halfway between the Rice and the B. So I wrote down my given information. And from that, I knew that AR was congruent to RM because of a midpoint. That's why I put those marks on there. And then I know that their segments are equal, so I said definition of congruent segments. And then since MB was the same as MB was the same as AR, I can substitute MB in its place. Since MB is the same as AR, I can take AR out of here and put MB in its place. So that's the substitution property of equality. And since MB equals RM, we can say that these two are congruent by definition of congruent segments. And then since they are congruent and M is the mid between them, that's the definition of a midpoint. That M is the midpoint of segment RB. Okay, so let's get into the right angles congruence theorem. Here's the theorem. All right angles are congruent. Well, you probably take that for granted because you know right angles are 90 degrees. So you think, well, they have to be congruent. Well, here's the proof for it. Well, since 1 and 2 are both right angles, I want to prove that they are congruent to each other. So first of all, what do I know? Well, they're right angles. So that's our given information, our first statement and reason. Next, what do I know about right angles? Well, they're 90 degrees. So measure of angle 1 is 90, and measure of angle 2 is 90. And that's what that little box in the corner means. So if I know they're 90, that's just because that's what I've learned what a right angle is. So now I can say that measure of angle 1 is equal to measure of 2 because they're both equal to 90 by the transitive property of equality. And since the measures of their angles are equal, I know that the angles are actually congruent. That's a definition of congruent angles. So that proves that theorem, and we can use that from now on. So if we want to use this theorem here to prove angle B is congruent to angle C, here's what I know. AB is perpendicular to BC, and DC is perpendicular to BC. So that would be the first thing that I could write down in my proof. Well, what do we know next? Well, what do you know about perpendicular lines? Well, perpendicular lines form right angles. Therefore, since AB and BC are perpendicular, angle B has to be a right angle. Same thing with angle C. Just what you know about perpendicular lines. You've learned that. So if they're right angles, I know that these angles have to be congruent because we just learned that all right angles are congruent. And if you want to write that as your reason, all right angles are congruent, you don't necessarily have to have this word for word theorem written down perfectly. Just say, I know all right angles are congruent. Okay, another thing that we deal with is the congruent supplements and congruent complements theorem. Hopefully you remember the term of supplements. Supplements are those angles that have a sum of 180 degrees. So think about it. If we have two angles supplementary to the same angle, or to the congruent angle, then, well, what do we know? So let's take a look at this. 1 is supplementary to angle 2, and angle 3 is supplementary to angle 2. What do you think is true about those two angles? Let's just pretend for a second. Let's say this is 30 degrees. 2 would have to be 150 degrees. And if 2 is 150, 3 would have to be 30 to make them supplementary. So I can see that 1 and 3 would have to be congruent. So angles supplementary to the same angle are congruent, is what we have come to find out. So if 1 and 2 are supplementary, 3 and 2 are supplementary, then we know that angle 1 and angle 3 are congruent. I'll just use my symbols there for that, so I don't have to write as much. Same thing. If 4 and 5, so 4 is complementary to 5 and 6 is complementary to 5. Let's say this is 30 degrees. This would have to be 60. And if this were 60, angle 6 would have to be 30 degrees in order for 5 and 6 to be complementary as well. So we'd say that two angles complementary to the same angle are congruent. And then we could say if 4 and 5 are complementary, 6 and 5 are complementary, and angle 4 is congruent to angle 6. Hopefully that makes sense and you can see that reason there. Okay, so let's prove that case of congruent supplements. 1 and 2 are supplements, 3 and 2 are supplements. We kind of work through a proof using one example, just throwing out 30 degrees and 150 degrees. But why does it work for all cases? Well, it's my given information. I know that. Well, what do I know about supplements? Well, supplements equal 180 degrees. By definition, that's what we've learned. So measure of 1 plus measure of 2 equals 180. Same thing, measure of 3 and 2 equal 180. So therefore, by the transitive property, I know 1 plus 2 equals 3 plus 2, because they both equal 180. So we can just set those equal to each other. And then by substitute or subtraction property of equality, I can subtract the measure of angle 2 from both sides. And what am I left with? Measure of angle 1 equals measure of angle 3. And if the angles are equal, I know that they have to be congruent, because that's the definition of congruent angles. If angles are equal, if their measures are equal, then the angles are congruent. Okay, I've got a proof started for you here. Why don't you try it out, pause the video, and see if you can fill in the corresponding statements and reasons. Okay, so since 1 and 2 are supplementary, 3 and 4, or 1 and 4 are supplementary, based on my given information, I know 2 and 4 have to be congruent because they're supplementary to the same angle, angle 1. So if they're congruent, measures of the angles are equal by definition of congruent angles. And notice here I put another bit of my given information. I didn't list it all at first. I could if I wanted to. If I wanted to move this up to step number 2, that is fine. But we didn't need it right away, so we just put it in here when we need it. So measure of 2 now I know is 45. So since I know 2 is 45, 2 is the same as 4, I know 4, measure of angle 4 has to equal 45 by way of the substitution property of equality. All right, so now let's take a look at GeoGebra and investigate what happens when we have intersecting lines, what's true with their angles. So in GeoGebra, we've got the measures of the angles. We have two intersecting lines, line AB and line CD, and they intersect at point E. Notice angle AEC and angle DEB are what we'd call vertical angles. Notice the measures of their angles are congruent. We'd also say AED and CEB are also vertical. Notice their measures of the angles are congruent as well. And if I change the angles, notice that remains true as well. Notice what also is true with angle CEA and angle AED. Look at the sum of their angles. What is always true? They're always supplementary. Same with angle AED and DEB. No matter what I do to those angles, these two are always supplementary. These two are always supplementary. These two, and same as these two. So we have 4 sets of supplementary angles, which we also term a linear pair because they're adjacent as well. So a linear pair are always 180 degrees. Vertical angles are always congruent. That sounds like something we should write into our notes. Okay, so if 2 angles form a linear pair, then they are supplementary. And since 1 and 2 in the example here form a linear pair, so 1 and 2 are supplementary, and measure of angle 1 plus measure of angle 2 equal 180 degrees. So that's always true with supplementary angles that form that linear pair. Vertical angle congruence, vertical angles are congruent. That's the symbol for congruence. So 2 and 4 are congruent, 1 and 3 are congruent. It's always true. Now, how do we prove that vertical angles are congruent always? Well, we looked at that example in GeoGebra, but that's not enough for a proof. So let's take what we know. We know 1 and 3 are vertical angles. So let's go from there. Here's a paragraph proof. So here's how I could prove that just in a paragraph form. Since 1 and 3 both create a linear pair when combined with angle 2, means that if the measurement of angle 2 is added to angle 1, or the measurement of 2 is added to measurement of angle 3, the total would be 180 for these two. So it implied that both the measure of angle 1 and 3 would be the same amount remaining to be added to angle 2. Kind of like that, what we're talking about with that congruent supplements theorem. So therefore, the angles would have to be congruent. This argument could be applied for any pair of vertical angles. So that's if you can just write out a logical argument. It doesn't have to be a 2-column proof. But if you want to write the 2-column proof, we list what we know. 1 and 3 are vertical angles. 1 and 2, I can look from the diagram, they form a linear pair. 3 and 2 form a linear pair. So it doesn't have to be told to me. I can just say, well, it's given in the figure. By definition, those are a linear pair. So 1 and 2 are supplementary, and 3 and 2 are supplementary because that's the definition of a linear pair. And so the measures of the angles equal 180, because that's the definition of what supplementary angles are. And therefore, since these equal 180 and those equal 180, by substitution we can say, or the transitive property, we can say that those are equal. Substitution property, we can eliminate measure of angle 2 to say that they are equal. If they're equal, this should be a congruent. Angle 1 is congruent to 3. Okay, so those are just 2 forms of proof that you can write. If you're more comfortable with the paragraph form, use that. If you like the 2-column proof, it's more of a logical person way to write it because you have the steps in order. If you're more, I guess, English-centered and you like to write, paragraph might come easier to you because you can just write down what you know. You don't have to worry about format as much. All right, so let's wrap it up. What do we know about a linear pair? QPT and angle QPR are a linear pair. So what is true about that? Well, the sums of their angles equal 180 degrees. So I could form an equation. 32 plus 3x plus 1 equals 180 degrees. Would be an equation that I could use in order to find out what the measure of x is. Okay, we don't need to solve it right now, but we've kind of worked with this in earlier units. Just apply what you know, which property is true about these angles. What kind of equation can I form? Are these 2 angles equal to each other? Do they form a sum of 180, a sum of 90? Do they add up to something else? So just take what you know and apply that. All right, so we talked a lot about proof and applying what we know about different angles. We learned about right angle congruence, congruent supplements, congruent complements, linear pair postulate, and vertical angle congruence. So a lot in this video, a lot to work through, but it provides us a good base for our future lessons. Talk to you later. Bye.